Hello, I'm SeungJeh from III Excel Lab. Today, I'd like to share a paper presented at SIGGRAPH 2025 by Microsoft about how attention mechanisms can be used for rendering. In other words, how we can use a pure transformer for rendering. The paper is called RenderFormer, and it's about transformer-based neural rendering of triangle meshes with global illumination. In generative AI, we can see a clear trend. Transformers have become the foundational model for major domains. For text, we have LLMs. For image and video generation, we have diffusion transformers. This begs the question, what about rendering? Can a transformer architecture solve this complex physical rendering as well? This paper proposes an answer, RenderFormer. Let's quickly review the two previous paradigms in rendering. First, we have traditional rendering. This is the physically based approach like path tracing that has been the golden standard in computer graphics for decades. It takes geometry, materials, lighting, and camera, and simulates the complex physics of light transport to produce a photorealistic image. The key advantage is its physical accuracy. The results are incredibly realistic. However, the major drawback is that it's slow and computationally expensive. To address this speed issue, the field moved toward neural rendering. A landmark example is NeRF. These methods run a continuous scene representation within the weights of a neural network. They are much faster at inference time and produce impressive results. However, they introduce a new critical problem, per-scene overfitting. This means you need to train a new network from scratch for every single new scene. This lack of generalization makes them impractical for many real-world applications. This is the key limitation that RenderFormer directly targets. So what is the goal of RenderFormer? It's to build a fully transformer-based rendering pipeline with three key properties. First, it requires no per-scene training or fine-tuning. This directly addresses the generalization problem. Second, it works end-to-end with classic triangle mesh input, just like a traditional renderer. And third, it aims to handle full global illumination. Essentially, the vision is a single model that takes a 3D scene and directly outputs a fully rendered image. The key idea is to reframe rendering as a sequence-to-sequence task. Let's look at the classic example, machine translation. A source sentence, which is a sequence of words, is encoded into a representation. The transformer then learns to map the source sequence to the target sequence. Then a decoder generates the target sentence, another sequence of words. This is a transformation from one sequence to another. Now let's look at 3D rendering again. Fundamentally, it's also a transformation process. It takes a complex 3D scene description as input and transforms it into a final 2D image. RenderFormer formulates rendering as a sequence-to-sequence transformation. The source sequence is a set of tokens, where each token represents a triangle with its initial material properties. The transformer then translates this into a target sequence. Each token in the target sequence represents the same triangle, but now it contains the final converged radians, the result of all global illumination effects. Now let's dive into the method. This is the full pipeline of RenderFormer. At a high level, it's a two-stage architecture that takes two primary inputs, the triangle mesh scene and the camera view. It then processes them through two specialized transformers to produce the final rendered image. First, the pipeline needs to process the 3D scene itself. So the initial step is to convert the classic triangle mesh into a sequence of tokens that the transformer can understand. Here's a closer look. Each triangle in the scene is converted into a triangle token. This token is a vector embedding all its essential properties, its surface normal, its material reflectance, and any emission if it's a light source. Crucially, its 3D position is encoded using relative spatial positioner embedding. This is the key mechanism for the transformer to understand the scene's geometry. As a result, RenderFormer can process native 3D input directly. The second input to the pipeline is the camera view. This information also needs to be tokenized. So based on the camera parameters, RenderFormer generates a ray map. For performance reasons, instead of processing individual rays, it groups them into ray bundles, where each bundle corresponds to an 8 by 8 pixel patch. The directions of these rays are then embedded into a ray bundle token. This creates a second sequence which represents the 2D camera view. Finally, with both the 3D scene sequence and the 2D view sequence prepared, the core rendering process begins. This is handled by the two main transformer stages. This simplified diagram clearly shows their distinct roles. The first, the view-independent transformer, takes the 3D scene sequence. Its only job is to solve the light transport. It calculates all the global illumination effects and outputs an updated sequence of lit triangle tokens. The second, the view-dependent transformer, performs the 3D to 2D conversion. It takes the 2D view sequence and, using cross-attention to access the lighting information from the first stage, it computes the final radiance values. These values are then passed to a DPT decoder, which stands for Dense Prediction Transformer, to produce the final rendered image. For those who are interested in the specific architecture details, I've summarized the key parameters and components on this slide. In short, it's a standard transformer architecture but with crucial adaptations for 3D rendering, like the custom positioner embedding and the use of cross-attention. I won't go through these in detail for the sake of time, but please feel free to leave a comments below if you have any questions. To train this model, RenderFormer is supervised using a combination of two loss functions. The primary loss is a standard L1 difference between the rendered image and the reference ground truth image. Additionally, to better match human perception, a small weight of the LPIPS loss is added. As you can see from these examples, this combines loss guides the model to produce results that are quantitatively and qualitatively very close to the reference. RenderFormer was trained on a large-scale synthetic dataset. Each scene are procedurally generated by placing 1 to 3 random objects from the observer's dataset into one of 4 template layouts. Key parameters like lighting, camera position, and material properties were all randomized within a wide range of well, within a wide range to ensure the model learns a robust representation of light transport. For instance, scenes could have up to 8 light sources and a maximum of around 4,000 triangles. In total, 16 million HDR images were rendered using Blender cycles to train the final model. Let's look at some research. I want you to pay close attention to the complex global illumination effects include soft shadow, subtle color bleeding, and glossy reflections. Here are examples of static and dynamic scenes. The model was trained on scenes with up to 4,000 triangles. As you can see, when we extrapolate to meshes with far more triangles, RenderFormer fails gracefully, preserving the overall lighting while losing some fine-grained shadow details. Similarly, the model handles more light than it was trained on, up to 8. Beyond that, it starts missing highlights, so the authors show this can be fixed by rendering each light separately and summing the results. RenderFormer also shows robust generalization for camera parameters. It produces stable and accurate results even when the camera's field of view and distance are pushed far outside the training range. Finally, let's look at resolution. When we render at resolutions higher than the training data, some minor errors appear, mostly around depth discontinuous continuities. However, the overall result remains coherent and visually plausible, again demonstrating the model's ability to fail gracefully. To conclude, let's discuss the current limitations and the future directions for this work. Of course, as an overall approach, RenderFormer has several key limitations. The most significant is the computational cost of attention mechanism, which limits the geometric complexity. The model is also currently constrained by its training data, lacking support for textures and more complex scene setups. However, these limitations open up compelling avenues for future research. The fully differentiable nature of the pipeline makes it a prime candidate for inverse rendering applications. To tackle the scalability issue, integrating hierarchical attention with classic structures like BVH is a very promising direction. And of course, expanding the training dataset will be key to supporting richer and more diverse scenes. Thank you for watching.